Have you ever wondered why Windows crashes more often than Linux? Or why Linux is used in everything from embedded devices to cloud servers and personal computers? And what exactly are the shell commands, and how does it work? In this video, let's learn about Linux's operating system and uncover all these secrets. After you watch this video, there will be an assignment. In the assignment, I'll guide you on how to use ByteBoss AI Agent to build your own AI-powered shell environment. With this shell, you can use your natural language to run a shell command in case you forget. My goal with these videos is to condense a full university-level computer science course into just 6 months. Once you finish all the sessions, you will not only have all the skills you should have, but also the skills to be a full-stack developer with AI's assistance, which would usually take years. To achieve this, it's not enough to just watch the videos. You need to complete all the assignments or projects as required. So let's get started. Understanding Linux operating systems, including topics like the bootloader, kernel, file system, and process management, can seem tough, especially for beginners. So let's break it down using the first principle rule. This means starting from the basics and building our understanding step by step, instead of jumping straight into complex concepts. Let's start by building and testing a simple Hello World program using GCC. GCC is a C language compiler and commonly used on Linux-like systems, even on Windows as well. First, compile the code with this GCC command. Then run the program. It will print Hello World. Next, let's inspect the Hello executable file by running this command. In the output, you'll see 3 main parts. On the left, you'll find the address, which shows the location inside the Hello binary. In the middle, you'll see the binary code instructions in hex format. This is the machine code that the CPU interprets. On the right, there's the assembly code. Assembly is a mnemonic, which is like a shorthand version of these instructions, making it easier for us to read and understand what's happening. Before we dive deeper into Linux OS, let's first think about how the CPU executes these instructions. Let's think about how a CPU can run an executable binary file. To keep it simple, imagine we only have 3 components: a CPU, memory, and an SD card for storage. First, we need to copy the file onto the SD card using a Flash MCU programmer. Since we don't have an operating system or copy shell command yet, this device is necessary to write data from your computer to the flash memory or SD card. Once the computer is powered on, the CPU reads the binary code from the SD card into memory and starts executing it. This is how a microcontroller unit, MCU, works. There's no need for an operating system. The CPU just loads the binary code directly and runs it. In this case, the Hello World binary file acts like firmware for the MCU. However, we can't simply take a binary compiled with GCC and run it on an MCU. That's because it's designed to run on a system with Linux. MCUs require a specific kind of compiler, called a cross-compiler, which can be used on Windows or Linux to compile code for the MCU. This process is known as cross-compiling, where you compile code on one system, like your computer, to run on a different system, like an MCU. The software on most embedded devices, smartphones, and modern computers is quite complex, and users often want the ability to install or update different operating systems. For example, you might have Windows on your computer, but decide to install Linux later. So how does the system handle this? This is where the bootloader comes in. It's a small piece of software similar to the Hello World binary or MCU firmware. After the bootloader starts and initializes the hardware, it loads the operating system. For embedded systems, a common bootloader is U-boot, while for Ubuntu Linux, the default bootloader is GRUB, Grand Unified Bootloader. The bootloader is stored at the very beginning of the storage device. But how does the CPU know where the storage device is? In many embedded systems, or SoC, system-on-chip devices, there's a small program called a boot ROM, or firmware built into the CPU itself. This is the first code that runs when the device is powered on or reset. It finds the storage device and hands over control to the bootloader. ROM stands for read-only memory, a type of memory that keeps data even when the device is turned off. On modern computers, this process is handled by BIOS, Basic Input-Output System, or UEFI, Unified Extensible Firmware Interface. These systems take care of initializing the hardware and then passing control to the bootloader on the storage device. UEFI has mostly replaced BIOS in newer computers because it offers more advanced features and better security. Now, let's dive into the Linux operating system. At the core of Linux, there are two main components, the Linux kernel and the root file system. Now that might sound a bit complex, but let's simplify it. Think of everything in Linux as different files. Imagine we have a mini Linux system with just 7 files and a storage disk split into 2 partitions. If we run the find command, it will list those 7 files like this. In this list, rc.local is a text file containing just one line, user sbin sshd. SSH is the secure shell application, and the D at the end stands for daemon. In Unix-like systems, daemon is a background service that runs continuously, waiting to perform tasks or respond to requests. The rest are binary files, similar to the Hello World binary we built earlier. We'll explain each file in detail later. Next, if you run the lsblk command to list all the block devices, which are storage devices that allow access to fixed-size data blocks, typically 512 bytes or more, it will display one device with 2 partitions, SDA1 and SDA2. Here's what this means. SDA is the first storage device. If there were more, they'd be labeled SDB, SDC, and so on. This device has 2 partitions, SDA1 and SDA2, which are mounted or linked to /boot and /. In the first partition, SDA1, under the /boot directory, there's only one file, vmlinux, which is the compressed Linux kernel. We call this the Linux kernel partition. In the second partition, SDA2, under /, you'll find the other 6 files. This is the Linux root file system, and the partition is called the root file system partition. Each partition, or even the whole disk, can be copied as an image file. An image is like a snapshot of the disk, capturing all the data, including the empty space. For most embedded Linux systems, there are 2 main image files, the kernel image and the root file system image. When updating the system's firmware, we write these 2 images to the correct partition. So what exactly is the Linux kernel? Technically, it's just a file, but it's not treated like regular files because it's the backbone of the whole system. The Linux kernel manages the hardware, processors, memory, and system resources. It hides the complexities of hardware from the user and developers, making the system easier to use. Here's why the Linux kernel is so important. It's the only part of the system that can directly interact with software. For users, interacting with a computer is all about working with files. The kernel handles everything happening in the background with the hardware. The kernel provides special functions called system calls for developers. For example, when you use the printf function in C or C++, you're actually making a system call. Any CPU, memory, or hardware-related operation goes through the kernel via system calls. All executable files in Linux rely on these system calls to communicate with the hardware. The Linux kernel is designed to be as small and efficient as possible to keep the system stable and easy to maintain. In simple terms, the Linux kernel acts as a bridge between the hardware and the user, so you don't have to worry about what's happening at the hardware level. In Linux, hardware is linked to device files, and you can either build a driver directly into the kernel or as a kernel module. A kernel module is code that can be loaded into the kernel as needed while the system is running. If the kernel doesn't recognize new hardware, you can simply load a module provided by the hardware manufacturer, or even build one yourself. It's similar to building a Hello World application. Once the module is ready, you load it using a simple shell command. We'll dive deeper into this topic in future videos. Once the Linux kernel is up and running, it executes the file sbin_init, which creates the first process in the system, known as process ID, PID1. This process, also known as the init process, is the parent of all other processes. The sbin_init process sets up the file system, starts other processes, and monitors them. In our mini Linux system, sbin_init reads the content of etc_rc.local, which stands for run commands, and launches the process user sbin sshd to allow remote access to the system via secure shell SSH. If SSHD crashes, init restarts it. sbin_init actually uses other configuration files to monitor and restart crashed processes. The command in etc_rc.local wouldn't automatically restart it if it crashes, but we're explaining it in this way to keep things simple. In modern Linux systems like Ubuntu, the systemd process has taken over the role of init. If you check the location of the init file with this command, you'll see that sbin_init is actually just a symbolic link to systemd. When a user-level application is run, like when sbin_init starts sshd, the system uses a system call like fork or clone in newer systems to ask the kernel to create a new process. The kernel assigns it a unique process ID, like 2 or any other number. The kernel then handles all the low-level work, like creating, scheduling, and managing memory for that process. When init or systemd creates a new process, it becomes the parent process, and the new one, like sshd, becomes the child process. Each process in Linux runs independently, in its own memory space, though parent and child processes can communicate if needed. If a parent process is killed, its child process can continue running. In such cases, the child process is automatically adopted by process ID 1, the init or systemd process. For example, in Android, which is based on Linux, if you start a background process that doesn't use any UI resources, even if the Android UI interface crashes, your background process will still keep running. However, the sbin_init process is special. If you kill the init process, it can crash or halt the entire system. In fact, some Linux systems won't even allow you to kill the init process using a command. In Linux, the kernel and user-level applications run in two separate memory spaces, kernel space and user space. User space applications can't access the kernel's memory directly. They can only interact with the kernel using system calls. So how do system calls actually work? A system call is essentially a CPU instruction. When an application makes a system call, it tells the CPU to request the Linux kernel to perform a function. For example, it might ask the kernel to create or terminate a process, or allocate free memory for the application. When we write programs in Linux, we're often writing code that interacts with these system calls, or the Linux API, Application Programming Interface. To learn more about any system call, you can use the man command in the Linux shell environment. For instance, if you run man printf, you'll see detailed information on how to use the printf function in coding. Man stands for manual. When we learn the C language with Linux, the most important thing is not just to learn C language syntax, but to learn and understand how the Linux system call functions work and how to use them, just as you would check the user manual for how to use an electronic device. Now, let's take a look at the root file system and the key directories in Linux. First, we have bin and sbin. The bin part stands for binary, which means executable files. Adding the S in front, just like in sbin, indicates system binaries. These are files meant for system-level tasks. Then we have user bin and user sbin. These are user-level directories. So when you see only the bin directory, it's related to system-level commands. When it's with the user directory, it's about user-level applications. Now, commands in sbin are generally reserved for system administrators, but normal users can run commands found in bin. Moving on, there's etc. Originally, this stood for etc., because it didn't quite fit into any category. Today, it's mostly used for configuration files. For example, you'll find the sshd configuration in the etc directory. To help remember, you can think of it as editable text configuration. Next is /dev. In Linux, everything hardware-related is treated as a device file. So in this folder, you'll find references to hardware components, like your CPU, disk, memory, and even your keyboard. Because Linux is a multi-user operating system, all user directories are under home. So, for example, you might see home Ubuntu or home Junior IT. The exception is the root user, whose directory is usually located in root. Finally, we have temp, which is used for temporary files. On devices like security cameras that rely on smaller, slower storage, like SD cards, temp is often mapped to internal memory. Keep in mind, any data saved here will be lost when the system reboots. You can access a Linux machine in different ways, through the terminal, using Telnet, SSH, or even a serial debug terminal. A serial terminal gives you direct access to the Linux machine's low-level console by using a serial port cable. This is especially useful when you're debugging embedded systems or accessing machines that don't have a keyboard, display, or network connection. But what exactly happens when you log into Linux through a terminal? The terminal runs the bash application for you, located in the user bin directory. What you're actually getting is the text input and output interface of the bash application. It's just like running any other application, like the classic Hello World example. The bash application reads your input from the keyboard and prints the output back to the terminal. Of course, bash isn't the only shell application we can use. There are other options, like bin sh and user bin zsh, which you also may encounter. In this video's assignment, I'll walk you through creating your own AI-powered shell using the ByteBoss AI Agent. When you run commands in bash, there are two types of commands you're dealing with. Real files, these are actual files in your file system. Commands like list, cat, grep, vim, find, and lsblk are all binary files or scripts located in the file system. You can use the command which list to find out where list is stored. It's usually at user bin list. Built-in commands. These are commands that the shell handles internally, without having to execute a file on disk. Examples of built-in commands include cd, echo, pwd, alias, exit, and history. You can check this with the command type cd, which will tell you cd is a shell built-in. Now, let's talk about two of the most important built-in commands. cd, which stands for change directory, and pwd, print working directory. Just like in other programs, shells have variables. These are called environment variables. Two important ones are path and pwd. The path environment variable is a list of directories that the shell searches when you try to run a command without giving it a full path. The pwd environment variable saves the location of your current working directory. The command pwd simply prints the value of the pwd environment variable. It's basically just running echo pwd behind the scenes. When you use cd to change directories, it's really just updating the pwd variable to reflect the new directory you're in. One thing to note is that the current directory is not included in your path by default for security reasons. If you want to run an executable from the current or a subdirectory, you need to use its relative or absolute path. For example, you'd use ./hello or test hello to run a file in those locations. When the bash shell starts, it first runs the configuration file in your home directory called .bashrc. You can edit this file to set your default search paths using the export path command. We've already explored the Linux kernel, the root file system, and even kernel modules. But since Linux is open source, have you ever wondered how to build Linux from the actual source code? There are several ways to do this, but today I'll introduce one of the most popular projects for building Linux from source, Buildroot. You can find it at buildroot.org or on GitHub. Buildroot makes the process a lot easier by providing a user-friendly menu that lets you select your CPU, your PCB board, and the hardware drivers you need. It then builds an entire embedded Linux system for you. After the build process is complete, you'll have all the necessary images, like the bootloader, kernel, and root file system. You can then use these images to burn an SD card and run Linux on an embedded device. In the description of this video, you'll find a link to join our Discord server. Once you're in, you'll get support from our AI assistant, ByteMate. Simply ask ByteMate for the free assignment that goes along with this video, and you'll get hands-on Linux exercises, covering everything in this video, from shell commands to the Linux kernel, kernel modules, and root file systems. In this assignment, you'll be building your own AI-powered shell environment with the help of the ByteBoss AI Agent, letting you interact with the shell using natural language commands. Even if you're new to Linux, as long as you've grasped the key concepts about the Linux shell, you'll be able to instruct the AI to do most of the work for you. If you found this video helpful, make sure to like it, subscribe to the channel, and hit the notification bell so you don't miss any upcoming videos where we dive deeper into Linux and AI-powered coding. See you in the next one!